All right. That's why we can at least record this. All right, it is recording. It's looking pretty good. That up. Okay. All right, for those of you who are already here, we're going to make this interactive. So if you've got your cell phone, you can go to joinpd.com, and then they're going to have you enter that little code NDVIQS. You can either use your actual name or nickname, depending on if you want to be honest about your responses or not. If you want to be snarky in your responses, probably put a different name. All right, we've got some calculations here. So if you've got a calculator. All right, I got some people still joining in, so. All right, hopefully it looks like just about everybody's on. So I'm going to go ahead and click start class. If you're joining late, we've still got that little code up there, so you can still hop in case you're not quite in yet. All right, let's go ahead and get started. So this is going to be about predicting eclipses and some of the other mathematics behind eclipses. And my name is Nancy Rakes, for those of you who don't know. So thank you very much for showing up. I really appreciate it. All right, so we've got a couple of questions and topics that we're going to cover in this. So we're going to start with just what is a solar eclipse? Some of the other things we're going to talk about is how often will we have a solar eclipse? How fast does an eclipse travel? What would happen if the moon were further away? And then we're just going to talk a little bit about some of the geometry of similar triangles and how that comes into eclipses. All right, so we're going to start with what is a solar eclipse. Some of you may already know. If you were at the talk with Mr. Eclipse, I don't want to repeat too much, but I want to just recap just a little bit in case anyone's not quite sure what it is. But basically, a solar eclipse is going to happen when the moon is directly between us on Earth and the sun. And essentially, the moon is covering our view of the sun. We've also got lunar eclipses. That's when the Earth is between the sun and the moon, and our shadow then is covering the moon. And so here we've just got a little bit of a picture, obviously not to scale here, but you can see the sun. So we've got the moon here and then the Earth, and we've got two types of shadows here. So we've got that very small inner shadow, which is the total eclipse. That's what we're going to have here. And then we have the much larger shadow, which is the partial eclipse. Partial eclipses are very common, as we'll see. Total eclipses, far less common. So here's the first question I've got for you is how often do solar eclipses occur? So if you're on the Pear Deck, you should have a couple of options there. Let's see if we can, does it show responses? So you've got responses once a day, once a month, once a year, something complicated. Got a thought? That is very specific. All right, I got a couple other people coming in. Nobody's going for once a day. You don't think it's daily?
No.
So sad.
Would that be nice? Is that what happens?
I mean, you could argue. All right, so looks like most people are going for something complicated. We got a couple other options in there. So let's talk about what actually has to happen for an eclipse to have. So again, technically all we need is, again, for the sun, the moon, and the earth to be in alignment. Now, it's not quite a month that the moon takes to go around. We say it's 27.3 days, or we call something called the synodic month, which is exactly the new moon to the new moon, which is about 29.5. So again, not quite a month, but pretty close to a month. However, unfortunately, for those of you who said every month, we do not have a total eclipse every month. So why not? It should occur every month, shouldn't it? You know?
It's because the moon rotates slightly every time.
Yeah, that's kind of what it is. So let's go ahead and pull that up and see how it looks. Basically, it's not perfectly in alignment. There's a little bit of a tilt. So there's a whole lot going on in this diagram. So we've got this dotted blue line. That's basically it's not actually the equator. It's the perpendicular to how we are rotating. And then we've got this little line here, this red line, that inclination, 5.14%. Basically, the moon is not rotating perfectly perpendicular to us. It's got that little bit of an angle going on. And here's kind of a picture that's showing it, which is, so sometimes when it's in that new moon phase, when I would normally have my total eclipse, is basically think of it as the moon shadow is missing the earth. So in this example, you can see the moon is above it. We obviously could also be below it, but basically that's why we don't always have a total eclipse, is because that shadow is missing us because of that angle. All right, so we are obviously having a total solar eclipse on April 8th. So when then is the next total solar eclipse? The next one is on August 12th of 2026, about 2.5 years from now. If you look at that picture, that dark area is where the total solar eclipse will occur. So you can see it's going through Greenland, just the very edge there of Iceland, and then through northern Spain as well. All right, so I thought we've got that next solar eclipse in about 2.5 years. Let's say we take one location. How often do we think a solar eclipse is going to occur in one particular location? And so I said, let's take London for an example, because I was able to find data for London pretty easily. And this is within 15 kilometers of central London. So from 1 CE to 3000 CE, so 3,000 years, there were 6 either have occurred or will occur. So that's about 1 every 500 years in one location. So they're pretty darn rare. All right, my next question, are we guaranteed to have solar eclipses? Will we definitely have them? Well, we can look at data in our own solar system at least. So not every planet in our solar system has a moon. So for example, Venus and Mercury don't have moons, so they can't have that type of eclipse because they don't have a moon. What about the others though? This is where I found some pretty cool pictures online. So this is a picture. It was taken from the Mars exploration mission. So this is one of the various rovers that we've sent to Mars. So this is actually a picture from Mars of the sun and then one of its 2 moons, Phobos, over the moon. Now, as you can see, this is not a total eclipse because Phobos is a very small moon, so it's not big enough to cover the entire sun. So it'd be considered a partial eclipse, but I thought that was an extremely cool picture. We also have them on the gas giants. Now, these are pictures that we took from satellites from space. Obviously, you can't stand on a gas giant because, you know, it's gas. And for this one, at least, you can see some of the shadows. So you can see one here, another here. That's, I believe, or maybe it's this one up here, I think that's just a spot on Jupiter. So those are 3 of the Galilean moons, so Io, Callisto, and Ganymede. Because as you might know, Jupiter has a lot of moons. Here's one of Saturn. Now in this picture, you can probably only see 2 of them. If you blew up the picture, I had to make it small to fit on the screen. There is one that's like right on the rings. Again, you can't quite see it here because it's small. And I think the other one was kind of also small. So again, you can't see all of them in this picture because I had to make it small. But there's actually a quadruple eclipse going on here with Saturn, with Titan, Mimas, Dione, and Enceladus. And then I got one more. So this one is from Uranus, and that is the moon Ariel. So there's another one. I was able to find a picture from Neptune, but it wasn't very high quality. But there are eclipses on Neptune as well, if you're curious. And again, all of these would not be considered total eclipses. They'd all be considered partial eclipses, but they do have moons, so they can at least have partial eclipses. I thought those were cool pictures. All right, this is about math. Let's talk about geometry. I know everybody loves geometry. So I am going to start with a couple of measurements. So the distance from Earth to the sun is approximately 93 million miles. It's a really, really long way. The distance from Earth to the moon is about 240,000. Now you'll notice I've got a couple other numbers in there as well. We're going to come back to that a little bit later and talk about that. But we do have a bit of a range there. And that is because an orbit is an ellipse. And again, we will look at that later. I'm also going to include the radius of both the moon and the sun. So the radius of the moon, so that's from the center to the edge, is 1,080. And the radius of the sun is 432,000 miles. So here, I've got a diagram. Once again, definitely not to scale here. So I've got the Earth. There's the moon, there's the sun. So on the sun, at least you can probably see that little X there in the middle. And then we're going up here. I'm calling this the tangent line. Those of you in my calculus class at least should hopefully remember tangent line. That's where we hit it in just the one place. So it makes a good place to draw for this diagram. Also, you'll notice they have slightly different numbers here. Depending on where you look, the numbers are slightly different. So you'll notice here they gave the diameter of the moon about 10 miles smaller. So there are a few different calculations depending on where you look. So what I'm going to do is I'm going to make 2 similar triangles. The first triangle is going to be from Earth to the moon, and the second one is going to be from Earth to the sun. And again, we're going to use that tangent point. So when a ray from the Earth will touch that moon or the sun in just that one place. So here's my little picture. Now you'll notice this point is not quite the tangent. We've kind of moved it up there just so that you can see it better. But we've got, so here R is the center of the sun. This B would be our tangent point. We've got P. You'll notice that's not in the middle of the Earth because I don't live in the middle of the Earth. I live on the edge of the Earth. And similarly, I've got the moon over here with Q and S. So again, PQ is the distance from me on Earth to the center of the moon. And similarly, PR is from me to the sun. PS, that is the distance from Earth to that tangent point. So if we have Neil Armstrong standing on the moon, that would be our tangent point. And similarly, PB is the tangent point to the moon. And then SQ is the radius of the moon. And RB is the radius of the sun. Then we've got some angles. Now we've obviously got a lot of angles here. This angle in particular, we're going to come back to and talk about a little bit more later. So we've got SPQ. So that's this little angle here, if you can see my cursor. And similarly, BPR, it's this angle. So I'm using that term angle of elevation. I know my math people will definitely be familiar with that term because I'm looking up. And again, so that's basically the angle that I am using as I'm standing on Earth to view that distance from the center of the moon to its edge, and similarly for the sun. And we call that the angular size of both the sun and the moon. And again, that's a super important number. We're going to come back to that number a little bit later. So for those of you who may not know, or just if it's been a while, what is a similar triangle? So first of all, the corresponding angles have to be equal. So here, my angle A and X are the same. C and Z, we've got 2 lines, they're equal. And B and Y, we've got those 3 lines, so those angles are also equal. The other thing we say about similar triangles, they don't have equal sides. We say that 2 corresponding sides have the same ratio. In other words, if we write them as a fraction, those fractions are equal. So if I take side AB and side XY, those are not equal. But if I put AB over BC, and then I took XY over YZ, those 2 fractions, those 2 ratios will be equal. So that's what we mean when we say a similar triangle. And again, you can see all 3 of those ratios for those of you that like to have them. So just bringing it back to my solar diagram. So again, all of the angles are going to be equal. And again, we've got then the ratios of the sides. Again, those ratios are also going to be equal. I wrote side just once there just to save a little bit of room there. So let's put in some of those measurements that we did earlier. So if we remember, the radius of the moon is about 1,080. The radius of the sun is about 432,000. And the distance from Earth to the center of the sun, as you might remember, we've got the distance from Earth to the edge of the sun, and then I'm going to add that radius. So I'm going to get 93,432,000 there. You'll notice I didn't do from Earth to moon because we're going to do that using computations. And for those of you with calculators, if you want to see if you get the same values, you're welcome to go ahead and crunch these numbers through with me. I'm going to go ahead and talk through what I'm doing. So again, SQ, that was the radius of the moon. PR, that's the distance from Earth to the center of the sun. And BR here, that was the radius of the sun. So that's where all of those numbers are coming from. And remember, if you've got 2 fractions equal, we are going to cross multiply. So I took the 43,000 times PQ is 1080 times 93,432,000, which is a very large number. That is 100,906,560,000. Yes, I used a calculator to get that. And then I divided both sides by 432,000 to get approximately 233,580. So that's the math I did. Let's see how well I did with my math. So again, that was the answer I just got for PQ, and that is in miles. And if we remember from earlier, we said the actual distance from Earth to the moon is about 240,000 miles. Now, obviously, I didn't put the radius of the moon into that equation, so we could put that in there as well. But I've also got this closest and furthest distance. We touched on that earlier. We didn't actually talk about what that is, though. We'll get there in just a moment. So again, as you can see, the number I computed versus the actual measurement, they're not quite the same. My number is a little bit off. Now it's pretty close. Again, it's not quite the same. We've got a couple reasons for that. You might remember when I had my solar diagram out, I had a slightly different number there for one of the values. So obviously, if I use different values for my measurements, my computation answer is going to be a little bit different. And let's touch on what happens if the moon is further away. Oh, is this one of the prompts? I think for some reason my prompts are supposed to be here. I'm not sure if you guys are getting these prompts or not. Yeah, you guys aren't getting these prompts. I'm not quite sure why. I was getting them when I tested this yesterday, so I apologize. You got one prompt at least. Well, this is the old version of my computations. I was going to skip that bit. Let me skip that little bit and go here. For some reason, my updated version of this did not go through. So we'll just skip those pages. Because I did want to talk about the fact that the moon has an elliptical orbit. We touched on this word earlier. So again, the moon does not rotate around the Earth in a perfect circle. It's something called an ellipse. Think of it as a circle that's kind of been flattened a little bit. And that's where those two numbers that we saw earlier, we've got the closest distance, which is called the perigee, which is about 225,600. And then the furthest distance, which is called the apogee, is about 252,100. And once again, this is definitely not to scale, but you can see we've got, this is not a perfect circle. So we've got that closer distance, and then we've got that further distance, because again, it is not rotating in a perfect circle. And similarly, when the Earth goes around the moon, we do not, or when the Earth goes around the sun, we do not go around the sun in a perfect circle either. That is an ellipse. And the other planets also travel in ellipses, not in actual circles. So, that was when, let me hop over to our calculation here. Oh, that was my extra calculation, which for some reason, I had a new version. For some reason, it is not showing up here when I'm on this computer. It's on my desk computer, so I apologize for that again. That was the extra computation I took out, so I am going to not worry about that too much. But basically, the number I got is within the actual perigee and the actual apogee. Basically, as we go through and we have ellipses, maybe it's going to occur at the perigee. Maybe it's going to occur at the apogee. Maybe it'll occur somewhere in between. So that's why we do have a little bit of error in there, because depending on how close the moon is, those numbers are going to change a little bit. And again, my numbers are within those parameters. So even though I didn't get the one exact number I was looking for, I'm within my range. So I should still be good to go. All right, so this was one of the fun things that I was hoping to work through with you guys, which is what happens if the moon was twice as far away. So I'm going to say the moon is the same size. We're not changing that, but we're going to have it go twice as far away. So as a reminder, the current distance is 240,000, and that 1080, that's the size of the moon. So now I'm going to say the moon is the same size, but it's further away. So now it's 480. And as a reminder, my measurement, I'm going to the center of the moon there, which is why I'm still adding in the radius of the moon. So let's take that same computation we did earlier and put in some of our numbers. These three numbers are all the same, but now I'm putting in my new value here. And again, that first value, that's the distance from me here on Earth to the center of the moon. And as you can see, we are definitely not getting the same number anymore. basically what's going on here? So we touched on this angle size earlier. So let's come back to that angle size. So again, because we have the similar triangles, we said that angle size has to be the same. And basically, this is why we have eclipses. As I stand here on Earth and I look up into the sky, the moon and the Earth, or the moon and the sun, they look like they're the exact same size because that angle size is exactly the same. So even though the sun is a lot bigger, because the distance further away is corresponding, that's why they look the same size. If they weren't the same size, we wouldn't necessarily have solar eclipses. But because they look the same size, it all works out. I'm going to make you do some trigonometry. So let's first cover what this is. I'm going to use something called a tangent. And for those of you who have never seen that, that is the Greek letter theta. That's just the variable that we like to use for angles. And we are going to define it as opposite over adjacent. So my little picture here, I'm looking at this angle. So its opposite side is this one, SQ, and its adjacent side is this one, PQ. Now we are taking the tangent of the angle. It's a type of function. So if I want to find just the angle, basically the way we undo that trig function, so to get rid of that tangent, we call it either the arctangent or the tan -1. So if you've got a calculator, if you look at the calculator, you should see that little tan button on it. And usually right above it, it's going to say tan -1. So if you've got a scientific calculator, it should have that on it. Were you able to find it? Awesome. So let's try putting in our calculations. Now, again, this is using the actual distance first. So again, there is my moon radius. And again, this is the current distance. So I took the arctangent of that. Now, if you get a different number, that's because you're probably in radian mode. I'm using degree mode up here just because most of us understand degrees a little bit better. But if you type in that tan -1 of that fraction, you should hopefully get at about 0.2567, and that is in degrees. Now that's a pretty teeny tiny angle. But again, the moon is really, really far away. All right, so let's remember that number. And that's not showing me my final value. Go away. So let's find that angle value of the sun. So again, I've got the radius of the sun, then I've got the distance of the sun, and once again, so I am now taking the arctangent once again of that ratio. And as you can see, this time I got 0.2649 degrees. As you can see, it's not quite the same, but once again, it's pretty darn close. And again, we've already touched on, depending on what measurements I use, my numbers might be a little bit off, but it's still pretty darn close. So again, that is more or less why those two appear to be the same size, is because that angular size is basically equal. So let's come back then and say, okay, so now what if we have the moon being twice as far away? So as a reminder, that's where that 48180. So again, my moon is the same size, but it's now twice as far away. So when I did the arctan of that particular ratio, I got 0.1286 degrees. And hopefully you'll agree with me, that is definitely not the same number. In fact, that's roughly half that number. So in other words, and this hopefully makes sense, if the moon was the same size, but twice as far away, it would appear roughly half the size if I were to look up into the sky. you may not know this, the moon is actually moving further away from the Earth. So it's not just a random question if I asked, what if the moon was further away? Because the moon is actually moving away from the Earth. Now it's moving incredibly slowly. It's moving at about 1.5 inches. That's about that much. That's pretty slow, but it is moving away. Now the sun is also getting larger. And for those of you who know astronomy, eventually the sun is going to get so big that it encompasses the Earth. And that 1 million years from now, I was going to skip that computation. So I'm going to hop past that one here real quick. We are eventually not going to have eclipses anymore. Now, there's a couple estimates that I was able to find. The one that is being proposed by NASA, at least, is approximately 563 million years from now. Basically, the moon will be so far away, we will still have partial eclipses. Again, we can have partial eclipses as long as we have the moon. But because the moon is going to be so small, we will no longer have total solar eclipses at that point. So mark your calendar, something to put down. Let me hit a couple other topics then. How fast does an eclipse travel? So what I used for my computation here is some data from the last total solar eclipse over North America. So this was, or actually I think this was 2 eclipses ago. So this was in August of 2017. And it hit quite a few places. I found 2 towns in Oregon, Newport, and I'm assuming you pronounce that Madras. And the 2 cities are about 144 miles apart. And basically, I found data where each town computed basically at what time did the eclipse start in this town, and then what time did the eclipse start in this town, at which point you just subtract those. So the time at which it was observed was about 0.0619 hours. So not a whole lot of time difference there. So here's a formula you might know. Distance equals rate times time. So I said those 2 cities are 144 miles apart. And again, the time that they computed was 0.0619 hours. So I divided both sides by that, and I got a speed of an eclipse of about 2,326 miles per hour. That is above the posted speed limit. That is very fast. Now, when I went to look up computations, again, I found a couple different numbers. The number, one of the numbers I found was 2,288 miles per hour, the speed at which the moon orbits the Earth. Again, as we see, we've got a little bit of error. And again, that's partly the computations I found. Also, for this one, we've got human error involved potentially, because if one town didn't correctly compute when the eclipse started, that would certainly affect our computations as well. So an eclipse is not a single point. I've got a picture here. This is from one of the satellites of basically the shadow of the moon on the Earth. And that's what's happening when we've got the eclipse. Now the diameter of that shadow, so from one end to the other, is about 68 miles. So fairly large shadow there. And again, as you might know, an eclipse does not last a single instant. If it was an instant, it would not be nearly as impressive, because you'd have to be looking at just the right moments. Generally, eclipses, roughly about 10 seconds at the shortest. The longest is about 7.5 minutes, a fairly long time there. So think of the time for the eclipse as basically the time for me to get from one edge of the circle all the way across its diameter to the other side of the circle. That's basically how long I'm in that shadow. And so that's how long I will experience my total eclipse. So I found a little picture here of the eclipse that's coming up. You can see Vincennes right in the middle. That's one of the reasons why the eclipse here is nice, is because we are literally, we're not only in the totality, we are basically in the center of the totality. So our eclipse, now this is the total eclipse. You've got the lead up and then the end of it as well. But the total eclipse time is going to be about 4 minutes and 5 seconds. Now, if you drive down to Evansville, you can see Evansville on the map. It's right there. It takes about an hour to get to Evansville. They will also have totality, but they're only going to have totality for 3 minutes and 5 seconds. And again, basically, for the reason for that is if you see those blue lines on my map, that's the line where you're still in totality. So Evansville is still within that band of totality, but unlike Vincennes, which is smack dab in the middle, so instead of, for example, going through the diameter of the circle, they're going through a chord of the circle. So that's why they've got a little bit less time than we do. If you're curious, I looked up online in Vincennes, when will the next solar eclipse occur? It will be October 17th, 2153. Mark your calendar. That way you don't have to move, right? I mean, otherwise you're going to have to travel to Greenland in about 2.5 years. You know, it's an excuse to go to Greenland. So. All right. And that is pretty much where I want it to end. There are a lot more computations. There's a lot more mathematics. I wanted to kind of hit more sort of the basic stuff, just because some of it can get very complicated very fast. But I hope you enjoyed it. And if anyone does have any questions. I had a version that had more jokes in it too. For some reason, it didn't load. So I apologize for that.
Thank you.
Thank you.